Algebra really is an extension of arithmetic operations. And the difference is that instead of using numbers as in arithmetic, we just assign letters to numbers. So for example, when we write 3x, what this really means is x stands for some number. It's a letter we're using to represent that number. And it means 3 times x. There's an implicit multiplication when we write 3x. And let's say if we write 5x squared, that means 5 times x times x. And again, the square referring to that there are 2 x's being multiplied. Now, one of the common steps you would need to do in almost all algebraic simplifications is to combine like terms. So anytime you have similar terms, you can always add them. So for example, if you have 5x squared plus 3x squared, they are really the same number, meaning that this is no different than 5 times a number plus 3 times another number. And how could we write that? So in this case, you could just simply say this is 8x squared. So if they have the similar expression, you can combine them. But if this was instead 5x squared plus 3x, we can't really simplify this anymore. You can't add these terms in any form. Now, what you could do is factor a common term, and this sort of goes back to what you could do with numbers. For example, if you have 12 plus 20, and we notice that both of these numbers are divisible by 4, so you can factor out a 4, and you would get 3 plus 5. We can do the same thing with that expression, and that's a common step you would be expected to know on the GRE. So here, and x is a common number because this is 5 times x times x. And then you say, what's left behind? We have 5x plus 3. So that's as far as we can go with that expression. Now, in general, if you're given a lot of different terms, and there are terms that could possibly be combined, always start by combining like terms. I would say in general, that's a good rule on the GRE. So for example, you're given something like 3x squared minus 7x squared plus 2x minus 5x plus 3xy plus xy. And here the like terms are the ones that have the similar algebraic expression. So 3x squared minus 7x squared becomes minus 4x squared, and then that becomes minus 3x, and these two become 4xy. So this type of simplification, anytime you have an opportunity, always do so. And if the expressions need to be factored, do so as well. So for example, this step is the opposite of factoring. So if you have something like 3x times x plus 2, you can think of these as a single number, and then you're adding 2 numbers, meaning this is no different than if I wrote 2 times 3 plus 5, which we can also write 2 times 3 plus 2 times 5. It works out to be the same number, 16. And here, it's really 2 times 8, which is also 16. We can do the same thing with algebra. So 3x times x would be 3x squared, and then 3x times 2 would be 6x. And another example would be, say, 4x squared minus 6x cubed. Here, the number they share, so if I write it the long way, it would be 4 times x minus 6 times x times x. And I say, okay, 2 x's are common, and then there's a 2 that also divides both 4 and 6. So I would factor 2x squared, and then I'm going to be left with 2 minus 3x. So these types of steps, always look for those. I'll give you an example of a problem where you have to implement that. So you're given that x is not equal to minus 1. And this is a quantitative comparison, quantity A and quantity B. On one side, you're given x squared plus x over x plus 1. On the other side, you have x. So we could certainly do this problem with numbers, but here they're really expecting you to see, can you simplify this expression and then sort of compare it with this. So here we notice in the numerator, we can factor in x, and it becomes x times x plus 1 over x plus 1. Now, this is a multiplication. So when you have a multiplication, you can strike out entire terms. So this is equivalent to x. What you can't do is, this is a common temptation a lot of students have, you can't strike numbers, numerator and denominator. So watch out for that. So in this case, after the simplification, quantity A is x, which is exactly the same as b. So here the answer is C. Both quantities are equal. So again, look to see if you can factor, simplify. Always do so. Another example would be you're given x times x minus 1 plus x is equal to 2x squared, and then you're given quantity A is x and quantity B is 0. So again, the clue is in this expression. There's a lot happening here, so the best strategy is to simplify and see where it goes. So we distribute those, so it becomes x squared minus x plus x equal to 2x squared. The x terms drop out. I get x squared equal to 2x squared. I can subtract x squared from both sides, and I'm going to get x squared equal to 0. This means that x is 0. So x as a number is 0, and both the quantities are equal. So the answer here is C. So these are some of the common examples where you need to simplify or rewrite an expression that is amenable to that. Another example is factoring, and here you're given quantity A and quantity B. So quantity A is 3x minus 6y over 3, and you have x minus 2y. So here I want to emphasize a common temptation is that students want to subtract something, divide these three. You can't do that. If you have a minus or a plus, don't ever strike out numbers. Instead, I would recommend to factor a common term in the numerator. So if I factor 3, I get 3 times x minus 2y over 3. Now this is a multiplication of these two terms and divided by 3. Now we can strike out the 3. So here again, quantity A and B, they're identical, and the correct answer is C. The other approach with this expression to simplify is you can divide each term by 3. So that's equivalent, and this would give you x minus 2y. So you can take either approach, factor or divide each term by the term in the denominator. So keep an eye on these types of temptations. Another example is which is also factoring, and especially using two variables. So a classic type of problem on the GRE is that they might give you an expression like this between the two variables x and y, and when you're given only one expression, we know that we don't have a unique value for x and y. It could be many numbers that would satisfy this relationship. And quantity A is y minus 2x, and quantity B is minus 3. So here, when they give you a combination of those variables in the quantity that you need to compare, a common temptation would be, well, I don't really know what x and y are, and so therefore I can't really answer this. But a common trap that they use on the GRE is that you can actually find the value for this expression even though we don't have a unique value for x and y, and perhaps these expressions are related. We may have to manipulate, so we'll try to make them look the same. So my goal would be to convert this to kind of look as much similar to that as possible. So I'm going to divide both sides by 4, and I get 2x minus y equal to minus 13 over 4. I have a minus y here and a plus 2x, so I know if I multiply both sides by minus 1, I'm going to get y minus 2x, and on the other side I'm going to get 13 over 4. And so quantity A, we actually have a unique value, and it's 13 over 4, and which is clearly greater than negative 3, so the answer here is A. So keep an eye on these types of expressions where you can find what they're asking for, even though you don't really know what x and y are. Just to reiterate the division, this part we did earlier, if you have A plus B over C, you can divide each term by C. That's acceptable, and it sort of comes from arithmetic. If you have 9 plus 6 over 3, we know that's 15 over 3. It needs to come out to be 5, and if you divide each term by 3, it does work out as 3 plus 2. Essentially what you're saying is if you have two piles of marbles. One has 9 and the other has 6, and you want to divide this entire stash into 3 equal parts. It's equivalent to dividing each stash separately and then adding the result. So that sort of is the basis. Whereas if this was A over B plus C, you can't do this as A over B plus A over C or something like that if you're dividing by a sum. Another slightly different example would be if you had AC plus B over C. Again, temptation might be to strike out these C's. You can't do that if you have a plus. Instead, divide each term by C. So you could do AC over C plus B over C. And now the C's can cancel, and then this becomes A plus B over C. So those are some of the common temptations that I've seen most students go for. The next concept is multiplying algebraic expressions. And these are terms that may be added. And so a good example of this would be something like this: x minus 3, 2x plus 1. So we have to do some kind of an expansion, but I want to go over what the basis is the distributive law. And what I want to show that this is a general form of a plus b times c plus d. Now we can think of a plus b as some number, and I'm just going to call it e. So when you have a number being multiplied over a sum, you can just distribute, meaning this would be the same as e times c plus e times d. And now e, which is this number a plus b, I'm just going to replace it. And now I'm going to distribute these numbers over a plus b. So this becomes ac plus bc plus ad plus bd. And so we get these 4 terms, which is really equivalent to carrying this operation by starting with the first term, multiplying with c, a times d. You'll see we get these terms. And then we distribute the b, so that gives me b plus c plus b times d. So easy way to remember, you start with the first term, multiply each one, then you move on to the second term, you multiply it with each term. So that sort of is the general approach, and that's what we'll take with the quadratic expression that I gave you earlier. So here, x minus 2 times 2x plus 1, you start with x times 2x is 2x squared, x times 1 is x, and then I get minus 2 times 2x would be minus 4x, and then I get a minus 2. Then I combine these two. Actually, these are the only 2 terms that can be combined, so that becomes minus 3x minus 2. So that's the approach you would be taking for simplifying quadratic expressions. Now, next I want to move on to identities. Now, identities are relationships that are true for all values of the variables. So that are true, meaning they hold true for all values of the variables, meaning if you used any numbers for the unknowns in the problem, and they will always hold true. So for example, a plus 2b is 2b plus a. They're identical. No matter what you select for a or b, this would always hold true. And there are 3 standard identities important for the GRE. The first one is the a plus b square, and I'll do the actual expansion here. A plus b times a plus b would be a square, and then plus ab plus ba plus b square. Now ab and ba are the same. When we multiply 2 numbers, they are the same. So we can add them and we get a square plus b square plus 2ab. I prefer to write it like this. A lot of books would write this term in the middle. It is really the same. So it's just a matter of preference. Now, I do want to give you a quick geometric explanation. This does help a lot of students. You don't necessarily need to know it, but it's just for making it a little bit easier to think about this relationship. So I'm going to draw a square, and then so this I'm going to call A. So this is a square that's a by a, and this is a square that's b by b. Now this is a, This is A, this is B. Now the area of this square here is A square. Area of this square is B square. This is a rectangle. This dimension is B. Its area is length times width. And here the area is A times B. Now this area of this larger square is just the sum of these components. So that's A squared plus B squared plus 2AB, because I have two of these. Now the outside dimensions here are A plus B, because it's A plus B. And its area is just square of that. And that's precisely the identity that we talked about. The other identity is the difference is that instead of A plus B, it's A minus B. So that identity is A minus B square, which is same as A minus B times A minus B. If you do the expansion here, you're going to get A square minus AB, that would be the second term, minus BA plus B square. And so the only difference is that instead of plus 2AB, you get a minus 2AB. And we can also do this or visualize this geometrically. And so here I'm going to call the outside dimension is A. This is B. So that's B. And so this becomes A minus B. And this is A minus B as well, because this is B. So the area of this square is A minus B square. Those are the dimensions. Here, this is A minus B. This area becomes B times A minus B. And this also becomes B times A minus B. And this is B square. So the sum of the area, or this area of this large square, would be A minus B square plus two of these, 2B times A minus B, plus B square, and that's equal to A square, because that's the outside dimension here. And so I'm going to write it as A minus B square. We can do this expansion, 2BA minus 2B square plus B square equal to A square. This becomes minus B square. And then I'm going to isolate A minus B square on one side, because this is minus B square. When I add to both sides, that becomes plus B square, and that is going to become minus 2AB. So we're back to our identity. The third identity is what's called the difference of squares. And the important thing about this identity is that you need to be able to recognize that in the exam, and it's a result of multiplying A plus B and A minus B. If we do the expansion here, we get A square minus AB, and then we get plus BA minus B square. And these terms, middle terms, cross out, and we end up with A square minus B square. And that's why it's called the difference of squares of two numbers. Now, this identity, again, means that this holds true for any two numbers. A and B could be anything. So, for example, if A was 5 and B was 3, if we replaced A and B with these numbers, this has to be true. So this 5 plus 3 is 8, 5 minus 3 is 2, and this is 25 minus 9, which is 16. And indeed, 8 times 2 is 16. So they are equal. Now, we can also visualize the difference of square identity. And the way to do that would be draw a square. And this outside dimension is A. And I'm going to draw inside square that has a dimension of B. So the area here would be B square. So A square would be the area of the large square. And so we're looking for A square minus B square, which is the shaded region. And we want to see if we can find that. So what we're going to do is to draw a dashed line here. I'm going to take this piece and extend it or rotate it. You can think of it as like I'm rotating it and bringing it here. So this dimension is A. That dimension is going to be, because I know that this whole thing is A, this dimension is actually just B. So Yeah, that would be different, but it's just b. And then this side, or the width of that rectangle, is going to be a minus b. So that's a minus b. So this piece, this entire piece here, is really the same as the shaded area. And the dimensions here, the length is a plus b, and then the width is a minus b. So it's equivalent to a plus b times a minus b. So some quick examples of how they would be tested on the GRE. And the first one was the identity where you're squaring the sum of two terms. Now you can certainly do the FOIL here, but that would be a little bit of a long method. I would encourage you to know the identity. And the way I would apply the identity here is that a plus b squared is the sum of squares of each term plus twice their product of each term. So here, when I apply that, 9x squared would be the first term because 3x times 3x is 9x squared. And then I get 4y squared plus their product would be 6xy, and then I double it, so it's 12xy. So that sort of just helps you in saving time and not have to do the expansion every time. So let's do a comparison here that's sort of based on this identity. Quantity A, quantity B, you're given that the product of xy is not equal to 0. Now this condition, when you see that, it just means that neither x nor y is 0. And here we have x minus y squared and x squared plus y squared. So again, if you see an opportunity for an expression to be expanded, always do so. This is the standard identity we did earlier. It becomes x squared plus y squared minus 2xy. Now this term is the same, so it really boils down to minus 2xy. Now xy, if xy is positive, then quantity b is bigger because you're subtracting a positive number. But if xy is negative, and that can happen if one is positive, the other is negative, this piece remains the same, but this is now positive because we have a minus here, and xy itself is negative. Now quantity a becomes bigger. So in this case, we actually don't have enough information. You can certainly do this problem using examples as well. That would be another strategy, but it's easier when you're using this general logic. One final example on the difference of squares is, which is, as I said earlier, is if you see expressions that conform to that form, always look to apply that. Now in this problem, the numbers I've given you here, you can't really use the calculator they provide you on the GRE because these numbers are too large. So I still think that they will likely give you sometimes problems where you can't use the calculator, but it does involve numbers. So first thing to notice here is that this is a difference of square of some number minus square another number. So we can write this as a plus b times a minus b. So this is 50,001 plus 49,999, and then we're subtracting them. So if we add these two, we get 100,000, and then that difference is just 2. And here, this is same as 10 to the power of 6. So column A is 2 times 10 to the power of 6, whereas column B is 2 times 10 to the 10 to the 5. So here, quantity A is bigger. So actually, I just noticed that I have only 5 zeros here. So actually, so one final example. So one final example on a difference of squares, which you need to recognize on the exam, is you're given quantity A, which is 50,001 square minus 49,999 square, and quantity B, which is 2 times 10 to the 5. So here you have to recognize that this has the same form as a squared minus b squared. Now, a squared minus b squared is equivalent to a plus b times a minus b. So here, a is 50,001 and b is 49,999. So we can rewrite this as 50,001 plus 49,999, and then 50,001 minus 49,999. Now this number here, I just have to add them. And be careful with the number of zeros. 1, 0, 1, 10, so that's 100,000. And then this is just 2. And 100,000 is same as 10 to the 5, because you just count the number of zeros. So this becomes 2 times 10 to the 5. So the two quantities are equal, and the correct answer here is C. So that concludes this section of the algebra lecture.